Well, the other one that we have looked at, or the next one that we looked at when we were looking at electric field lines, was for a dipole. So let's see if we can figure out what the equipotential lines look like for a dipole. Well, we've got a positive charge, so let's say plus Q, a negative charge minus Q. And what we know is the electric field lines go from the positive charge to the negative charge, something like this. Okay, there we go. So those are the electric field lines. That's what we came up with last time when we were looking at electric field line diagrams. Let's see if we can figure out what the equipotential lines will look like. Well, what we're going to do is just basically draw in lines that are always perpendicular to the electric field lines. Now, right through the middle, we know the electric field lines are all horizontal. So from symmetry, we know they're all horizontal at that point. So we know that a perpendicular line will always just be straight up and down. So I'll draw in little perpendicular lines to every electric field line, and then we'll connect those up, and basically there is an equipotential line. It goes right down, straight up and down through the middle. Now next to that, we might draw in some little perpendicular lines, and granted, I'm kind of putting these in knowing a little bit what they're supposed to look like. And then we can connect these up like that. And then again, we end up with something that looks something like that, and like this, and like this. Okay, hopefully these are supposed to all be perpendicular. And something maybe like this, something like this. There we go. Now, again, there's a freedom to define whatever we want as our zero potential. We define the infinite distance as our zero potential for our point charge for KQ over R. In here, typically what's often done is we'll define this symmetric point in the middle as zero. So here's our zero voltage. And then towards or near the positive charge, we'll have positive voltages. So say this might be something like 10 volts, 20 volts, 30 volts. And closer to the negative charge, we'll have negative values, so negative 10 volts, negative 20 volts, negative 30 volts, something like that, okay? And what I want us to just notice is that in here, notice our equipotential lines are close together. And what does that tell us? When the equipotential lines are close together, we have a lot of force, in other words, strong electric field. While over here, they're further apart. Likewise, the electric field lines are further apart. And what do we know over here? We have a weaker electric field. Okay? When the field lines are far apart, we have a weak field. When they're close together, stronger field. Okay? So there we go. That gives us an idea of what the potential looks like near this dipole. One thing we might think about, just a slightly different way of thinking about what this looked like, is looking at the magnitude of the value of the potential. For point charge, we have that V is equal to KQ over R. If we were to sketch this, what we would end up with is maybe kind of something like this from one side to the other. We might think of the positive charge here at the origin as creating kind of a hillside, a very, very steep hillside that basically goes up to infinity, so to speak, as R goes to 0. And then for a dipole, we end up with something like this, say positive charge here, negative charge here. We have this very sharp peak near the positive charge, and then a very steep hole in the ground near the negative charge. So the positive charge creates this this very sharp mountain of positive potential, while the negative charge creates this very sharp hole in the ground, going down to an infinitely sharp hole in the ground at the location of the negative charge. Okay? So it's just another way of thinking about the form of these potentials. Okay, so what I'd like to do now is go back and take a look at capacitors. We started to take a look at those last time. And let's see what happens when we actually put some material inside a capacitor. What kind of an effect does that have on the capacitor itself and the capacitance of the capacitor? Okay, so let's remember what we talked about last time. Let's imagine that we have a parallel plate capacitor, which is essentially two plates, two parallel plates. But remember that these plates need to be close together. Close together meaning the distance between them has to be small compared to the length and width of the plates. So let's imagine that we've got, say, two plates. Here are two plates, and let's imagine that the distance between them is maybe some value of d, and the area of each plate is A. And let's imagine that each one has, say, the top one has a charge of plus Q, and the bottom one has a charge of minus Q. Remember, this is kind of like a dipole, but the charges have been stretched out into a flat surface. And what this creates then is an electric field in between the plates that is very uniform, pointing from the positive charge to the negative charge. And what we found last time is that the value of the electric field, so this is the electric field in there, the magnitude of the electric field was equal to sigma, which was the charge density, the surface charge density, which was the charge per area, divided by epsilon naught. And remember, epsilon naught was the permittivity of free space, which is 1 over k, where 1 over 4 pi k, where k is Coulomb's constant. All right, now, remember when we were talking about the potential between 2 points, what we had was that the change in the potential energy we could find, which was equal to the work done if we move an object from one point to another, and that is equal to the force times the displacement times the cosine of the angle between them. Now I want to think about, let's imagine we move, say, some charge, some little q, and we take this little q from the negative plate and move it up to the positive plate. The amount of work that we would have to do would be the force. Now if we've got some little charge of plus q, the force acting on it, we know, will be little q times the electric field. Remember, we defined the electric field as the force per charge, so the force will be the charge times the electric field. So what we'll have is the force done will be, the force acting on it will be q times the electric field. And let's move it all the way from one plate to the other. In other words, we're going to move it a distance d. So that'll be our displacement. So times d. And let's assume that we're moving it exactly opposite the electric field. So the force that we are applying is in the same direction as the displacement. So we'll have cosine of 0 degrees. Cosine of 0 is 1. And there we go. So there is the change in the potential energy. So what is the change in the potential? Well, that's going to be the change in the potential energy per charge, which leaves us with the electric field times d. In other words, sigma times the distance over epsilon naught, or q over a times the distance over epsilon naught. Okay, there we go. Now let me erase most of this and put that down, because that's the important part I want to talk about right now. If we have a capacitor with a voltage between the plates of V, that voltage is equal to QD over A epsilon naught. Now I want to rewrite this a little bit. I want to take this part I'm going to leave the Q and take this part and put it over with the V. So we end up with Q is equal to A epsilon naught over D times V. And there we go. That's what I want to look at. This quantity depends only on the physical structure of the capacitor, the area of the structure, the area of the plates of the capacitor, the distance between the plates, and epsilon naught, the permittivity of free space. This is then whatever charge we put on the capacitor, and this is then the voltage that we end up with across the plates of the capacitor. This quantity here is what we call the capacitance. The capacitance of the capacitor. And we will label this with a capital letter C. Now, I am sorry, do not confuse the capital letter C for capacitance with the capital C for coulombs. Now, in this case, I'm actually going to put a little subscript O here because the assumption at this point is that there's nothing in between the plates. In other words, we'll assume that there's nothing in there but a vacuum. We might refer to this as a vacuum-filled capacitor. That might sound a little funny, vacuum-filled, because a vacuum means nothing. So it's a capacitor filled with nothing. So a vacuum-filled capacitance, this will be the vacuum capacitance of the capacitor. To emphasize that this is then the charge on a vacuum-filled capacitor and the voltage across the vacuum-filled capacitor, I'll actually write this equation now as Q naught equals C naught V naught. So this is an equation that relates the charge, the capacitance, and the voltage across a vacuum-filled capacitor. Now, okay, so let's keep that in mind. Now, let's imagine that we actually put something in here. Let's fill this capacitor with some material. And let's see if we can figure out, well, let's think about what might happen if we do that. Okay, I'm going to bring up a picture of a capacitor. Okay, so here we go. Here's a capacitor. Let's imagine we've got a positive plate over here with some charge of plus Q, a negative plate over here with some charge of negative Q, and these lines represent the electric field lines. So we've got an electric field pointing from the positive plate to the negative plate, and it's uniform, relatively uniform within the plate. Once we get up near the edge, we start having some curving, just like the lines curving around at a dipole. But let's kind of ignore those edge effects. Let's imagine we've just got some constant electric field in between the plates. Now let's imagine we put some material in here. And let's imagine this material is made up of some kind of molecule, perhaps like this one. Now you can imagine this might be, say this was a sodium chloride or salt molecule that hasn't disassociated in water or something like that. Let's just imagine we've got some molecule like this that's still stuck together, where this might be a sodium atom, this might be a chlorine atom. Now, if you've had chemistry, you might know that a molecule like this, the charges have redistributed themselves a little bit so that the chlorine has a net negative charge and the sodium has a net positive charge. So this is actually just like a little tiny dipole. We've got a positive end and a negative end. Now let's imagine we put this thing into in the space between our plates. What's going to happen? Well, there's going to be a force on the two charges. The positive charge will experience a force in the same direction as the electric field. In other words, it will be attracted to the negative plate. The negative charge will experience a force in the opposite direction to the electric field. It will be attracted to the positive plate. So what's going to happen to this thing? It's going to align itself with the electric field, like this. Now, if the electric field is uniform, the force on the positive charge will be exactly opposite the force on the negative charge, so it's not going to move one way or another. Now, if the forces were different, we might end up with some net motion. But if the forces are the same, the only result will be to align the molecule with the electric field. So that's what would happen if we had a dipole molecule, a molecule with what we would say a dipole moment. it would align itself. Now, let's imagine we have maybe a little more complicated molecule, something like this. So this might be, say, a water molecule where we have two H's and one oxygen molecule, two hydrogen atoms, one oxygen atom. Now, in this case, the negative charges are pulled away from the hydrogens, leaving the hydrogens with a net positive charge, the oxygen with a net negative charge, meaning that this end of the molecule has a net positive charge and this end has a net negative charge. So again, we've got a dipole molecule, although the structure is a little bit more complicated. And again, if we were to put this in here, what would happen? Well, those hydrogens would be attracted to the negative plate and it would align itself like this. The oxygen being attracted to the positive plate, the hydrogens being attracted to the negative plate. So again, the dipole would align itself with the electric field. Well, we might have something like this. Now, what could we imagine this one would be? Well, if we had, say, one carbon atom and two oxygens, this might be, say, carbon dioxide. Now, in this case, the oxygens are again negative with a net negative charge. The carbon has a net positive charge. In this case, we do not have a dipole moment. It is not, there is no dipole arrangement that we have seen before. So what would happen if we put this in here? Well, the oxygens again would be attracted to the positive plate, right? Oxygens negative charge, so they're attracted to the positive plate. The carbon would be attracted to the negative plate. So what would happen in this case? Well, these would actually slightly distort themselves. Well, when it distorts itself, then we end up with a negative end up here and a positive end down here. And so we still end up with a slight dipole moment. So even though the molecule originally did not have a dipole moment before we put it in the electric field, after we put it in the electric field, the molecule distorts itself to some extent and creates a dipole moment. So the electric field actually induces a dipole moment in the molecule once we put it into the field. Okay, so let's imagine whatever we do, we put some molecule, some material in here, whether it has a dipole moment to begin with or a dipole moment is induced in the material after we put it in the electric field. Let's imagine we've got some material that does that in here. So what happens? Okay, here we go. So all of those dipoles in there align themselves with the electric field. All the negative end of the dipoles pulled over toward the positive plate. All the positive end of the dipoles pulled over toward the negative plate. And in here, these positives and negatives tend to cancel each other out. Canceling each other out, canceling each other out, except we end up with, on one side, these lines of negative charges, and on the other side, this line of positive charges. These negative charges have the tendency of canceling out some of the positive charges over on this side, and the positive charges over here have a tendency to cancel out some of the negative charges on this side. And what we end up with then is something like this, where the negative charges cancel out some of these, the positive charges cancel out some of these. We end up with a weaker electric field between the plates. The electric field is not as strong as it was when there were no dipoles in between here. Well, with a weaker electric field, what happens? The potential between the plates is smaller. We have a smaller difference of potential between the two plates. So what does that mean?